Today we are going to look at Chapter 9, Simple Harmonic Motions, also known as SHM. So this topic, it consists of three subtopics: 9.1, Kinematics of Simple Harmonic Motions, 9.2, Graph of Simple Harmonic Motions, and 9.3, Periods of Simple Harmonic Motions. So for today's lessons, we're just going to focus on 9.1, Kinematics of Simple Harmonic Motions. We're going to have a basic idea on how an object can move in a simple harmonic motions, how to tell whether an object it moves with a simple harmonic motions or not, it exhibits the characteristics of simple harmonic motions or not. So that is our main focus today. So what does it mean by simple harmonic motions? In any oscillating system for which the net restoring force is directly proportional to the negative of displacement, it says to exhibit simple harmonic motions. What does it mean? Well, it means that the magnitude of net restoring force is directly proportional to the magnitude of displacement. But then, what is the purpose of this negative? What does it mean by this negative? Well, this negative simply means that the directions of net restoring force and the directions of a displacement is always opposite to each other. Okay, so meaning that their magnitude they increase, both of them they are going to increase at the same time, but then towards opposite directions. So for example, let's look at the motions of a spring. We know the motions of a spring, the force inside the spring is F equals to negative kx. Now, if you apply Newton's second law, where summations F equals to ma, therefore negative x is equals to ma. Rearrange these equations, you're going to get A equals to negative k over mx, where k is a force constant of a restoring force, or in this case, it is known as spring constant, and m is the mass of an object. Well, these two variables, they are always constant if you're using the same springs and also the same mass, same block. Okay, meaning that if these two, they are constant, okay, in these equations, then A and X, they are dependent on each other. So A will changes with X or X changes with A. With a negative sign here means that the directions of A is always opposite to the directions of X. Okay, which means that the motions of a spring, it exhibits the simple harmonic motions pattern. So instead of saying that the net restoring force is proportional to the negative displacement when an object moves with simple harmonic motions, most of the times we would say that an object moves with simple harmonic motions if its acceleration is proportional to its positions and is oppositely directed to the displacement from equilibrium. So A is directly proportional to negative x. This is the terms that we often use when we describe simple harmonic motions, or when we check whether an object exhibits simple harmonic motions or not. Now, what does it mean by equilibrium positions? Because the definitions tells you that A is oppositely directed to the D, okay, to the displacement, to the X. So from equilibrium. So what does it mean by equilibrium positions? The equilibrium position is a position at which the body would come to rest. Meaning that if you hang an object in a springs, or if you have a swinging pendulum, the place after you release it, when it comes to rest, that one we call it equilibrium positions. The positions that the object won't move, object stop moving, object stay at rest. We call it equilibrium positions. Okay, and then the maximum excursions from the equilibriums. Okay, maximum excursions is the maximum displacement from equilibrium is amplitude. We call it amplitude. Before it reaches maximum displacement, we just use the term displacement. Okay, we use symbol x to represent the distance traveled by the object, or we use displacements to describe it. But when it reaches the maximum displacement, we use symbol A to represent it, to tell the reader that now the object has reached its maximum displacement. It won't be able to go up anymore. It won't be able to go further anymore. Okay, and this is what I told you just now. The negative sign indicates that the directions of the acceleration is always opposite to the directions of the displacement. So that is the meanings of the negative sign in our relationships here. Alright, so this is the examples that I mentioned just now. Okay, when you have an object oscillating with a spring. So let's look at the diagram B. Okay, diagram B, now you attach an object, a mass, to the spring. Okay, maybe initially maybe it will oscillate a few cycles, but when it's stored, this is where we call equilibrium positions. okay, when it is not moving. So if you pull the objects to the right of the equilibrium, means you're increasing its displacement. Okay, you increase its displacement. So the displacement is going to the right. But then if you look at the F, okay, the restoring force, what does it mean by restoring force? Restoring force means it is the force that trying to bring the object back to its original positions. So if you pull the object to the right, then restoring force is heading to the left. So restoring force is equals to MA, let's say, okay, meaning that my A is now going to the left. So based on this diagram, my A is directly proportional to negative X, which tells us that this spring it exhibits simple harmonic motions. Okay, because A increased when you pull the object further away from the equilibrium positions. Well, obviously, why? Because the restoring force is getting bigger and they are heading towards opposite directions. So this is a form of simple harmonic motions. Now, how about this case, diagram C? Diagram C, you push the block to the left-hand side. So let's say the X is going to the left now. Restoring force is now going to the right. Why? Because it tried to push the object back to its original positions. In other words, my A is going to the right. So in this case, I still have A is equals to negative X. So this object is still moving with simple harmonic motions. Therefore, horizontal spring is a typical case of simple harmonic motions. So when an object moves in a simple harmonic motions, we can use a graph to represent its motions. Okay, so this graph is X against T, X against time. So when the time goes by, this is the displacement traveled by the object. This is the distance traveled by the object. So displacement is the distance from equilibrium positions to its current position. If you look at it as a whole, this is the distance traveled by the object. Okay, and if you notice, the A and the negative A here, they have the same magnitude, and the magnitude is a fixed. Okay, whenever it's located at A, they all are going to have the same value. Why? Because we assume there's no frictional force and we assume there's no air resistance acting on the object. Then how about the positive and negative value? How do we know that they are the same? Now let's look at this oscillating pendulum bob. Okay, this is a typical examples. Now we can see what happens to the object. Let's look at it in terms of its energy. When the object is at a maximum height, we say the maximum, it has a maximum potential energy, whereas K is equals to 0. Why? Because objects stop moving at maximum height. Okay? So, and when we release the object and it reaches the lowest point, what is going to happen? At lowest point, it has a maximum kinetic energy. Okay, all of the potential energy has been transformed into kinetic energy. How do I know? Because we take the lowest point as h equals to 0. And when h equals to 0, my u is also equals to 0. Meaning that all force or energy has been transformed into kinetic energy. So after it passes the in equilibrium position, it will keep moving up again. Okay, until it reaches the maximum height, and at this point all of the kinetic energy has been transformed back into potential energy. So at this point we have maximum potential energy and K is equals to 0. So amount of energy is fixed. Okay, amount of energy is fixed, means that the maximum height that it can reach is same as the height as its initial positions. It won't go any higher. Okay, and since there's no energy loss, so the height would be the same. Okay, unless it has energy loss, then the final positions, the negative A, might decrease. Or else, positive A and negative A, they are always equal because of the energy inside the spring is constant. So we're going to look at 3 examples in these chapters, 3 examples that exhibits the characteristics of simple harmonic motions. The first one is the horizontal springs. So this is a piece of papers. It is being attached to 2 rollers. So this roller will keep rolling the papers, and meaning that the paper will keep moving upwards as the object oscillates. So we are trying to record the path traveled by this oscillating system, this horizontal spring. So this horizontal spring is being attached to a pendulum bob, and a pen is being attached to the pendulum bob as well. So now you pull the springs to its maximum displacement and you release it. Okay, so the papers will record the path traveled by the springs. So after certain moments, when you look at the papers, it will generate a sine graph like this. Okay, it will generate a sine graph like this. So this shows that the object is moving with simple harmonic motions. Okay, so another example would be the vertical spring. Okay, vertical springs, you're going to do it with the same method. You put a piece of papers, you attach a piece of paper to two rollers. So the paper will keep moving to the right as the spring oscillates. Then you can record the path traveled by it. So again, it is a sine wave, okay, sine graph functions. Now, how about a swinging pendulum? Once again, you attach a piece of paper to two rollers. So this paper will keep moving to the left as this pendulum bob oscillating. Once again, as you can see, it's going to generate another sine graph here. Okay, another sine functions here. One way to visualize the graph of simple harmonic motions is by using reference circles. So you have a flumps here, it's being attached to two rollers, same as the previous case. So it will keep moving upwards. And in front of the flumps, what do we have? We have a disc that keeps rotating at a constant speed. Then you put a pendulum bob on top of it, and here you just have a rows of light that is parallel to the pendulum bob. Okay, so it will just shine on this line. So what happens here is when this reference circles rotating, okay, when it rotates, it will generate a simple harmonic motions graph at the back on the flump. Okay, now let's try to look at this diagram. What happens now is, if you look at this diagram, when your pendulum bob is at point O, okay, let's take it as the origin. Okay, the origins of the simple harmonic graph. So when angular displacement increase, the displacements of the simple harmonic motions also increase. So when it reaches the 90 degree, this graph also reaches its maximum displacement, which is the amplitude, meaning that the angles for the amplitude is 90 degree. Okay, it is located at pi over 2 radian. So after it passes through the 90 degree, okay, it moves towards 180 degree. When it reaches 180 degree, simple harmonic motions also goes back to the origin. Okay, so it is the same line. It is the projections, as you can see here. So when it decreases, goes towards the 270 degree. Okay, when it goes down, the graph of simple harmonic motions also going down until it reaches maximum amplitude, maximum negative amplitude. Okay, so when it goes back to the origin, okay, as you can see here, the displacement, it goes back up. Here, the displacements, the graph also goes back up until it goes back to 0. So when it reaches this point, we say the object has completed one cycles, one revolution, which is 360 degree. So meaning that from O to A is 90 degree or pi over 2 radian. And then from O until it goes back to the origin, this is 180 degree, or we say pi radian. Okay, and then this is negative pi over 2 radian, or negative 90 degree. When it goes back to the origin, this is 360 degree, or 2 pi radian. So the time taken to complete this one cycles, we call it period. So based on the graph generated just now, okay, we can see that it produces a sinusoidal functions. Therefore, we can use x equals to a sine theta to represent the motions if the object is start from equilibrium. So this theta, it must be in radian, yeah? The SI unit for theta must be in radian, not unit. The object in the reference cycle is rotating with uniform angular velocity. Therefore, we can write theta equals to omega t. Okay, and this is what we have seen in 8.1, okay, chapter 8.1, where we said omega is equals to theta over t. So now you just rearrange it in order to obtain these equations. So x can be written as a sine omega t as well, where omega t is known as phase. So in general, at times t equals to 0, x is equals to 0. Why? Because sine 0 is equals to 0. Okay, sine 0 degree is equals to 0. Therefore, at times t equals to 0, x will be equals to 0. So this one, we assume motion start from equilibrium. So what if the motion is not start from equilibrium? So if the motion is not start from equilibrium, it means that at times t equals to 0, x is not equals to 0, right? Because you look at the graph. Okay, now if you have a graph of x against t, this is a graph of x against t. If t equals to 0, s does not start from 0, meaning that it starts either from the positive displacement or negative displacement. So in this case, the equation should be written as x equals to a sine omega t plus phi. Okay, some of you like to call it phi, then I call it phi. So it's up to you whether you want to call it phi or phi. But the most important thing is you know that this symbol, it represents initial phase angle. Okay, the word initial means it tells you the initial positions of the object. So now the object, it does not start from 0, so it must have an initial displacement. So it tells you where that it start from. So x equals to a sine omega t plus phi. And this whole thing, okay, this whole thing, omega t plus phi, we call it phase angle. Okay, now not just omega t, but omega t plus phi, this whole thing is known as phase angle. Now let's look at the first diagram. Okay, first diagram, my object at times t equals to 0, okay, at t equals to 0, x equals to 0. So in this case, I have object that start from origin. Therefore, I use x equals to a sine omega t. This second diagram, I have an inverted sine function. Therefore, I add a negative sign here. So x equals to negative a sine omega t. Now, how about this one? This one, you have an initial phase angle, okay, initial phase angle. So now you have a negative displacement. It tells you that your object starts from negative angular displacement. Therefore, we put a negative sign at your initial phase angle, okay? It means that your object starts from negative. Do you still remember when you have a circle just now? Okay, this is a circle that we have in the previous page. So when objects start here, then we have a negative sine graph. Okay, so this is your sine graph. So your object start here. So mean it is negative theta. Okay, negative angular displacement. Therefore, in your equations, you use negative radian. So whereas for the last graph, okay, for the last graph, we have a positive sign here. So why positive sign? Because now your object start from positive angular displacement. Okay, it starts from somewhere here, positive. So just now we have negative, now we have positive. Therefore, I use plus theta in the equations. Okay, so you compare the graph, you look at the graph starts from positive, so I plus theta here. The graph starts from negative, so it's a minus theta here.